Imagine an AI, right? But not the kind that just sits in a text box drafting your emails or, I don't know, writing Python code.
Right, something way more active.
Exactly. We're talking about an AI that is, as we speak, currently running around in a game like Goat Simulator 3.
Which is just absolute 3D chaos.
It really is, and it's navigating that chaos, playing the game exactly like you or I would. And, this isn't science fiction. It's happening right now on Google DeepMind's servers.
It's pretty wild to watch.
So, welcome to today's deep dive. If you're someone who loves connecting the dots on where tech is heading, you are in the right place. Today, we are focusing entirely on a single, just fascinating technical report from December 2025.
Right, from DeepMind.
Yep, titled SIMA 2, a generalist embodied agent for virtual worlds. And our mission for this deep dive is to really map out this massive leap that's happening in artificial intelligence right now.
Because we're watching this real-time transition from, passive chatbots that just talk at you to what researchers are calling embodied agents.
Embodied agents.
Right. Yeah, models that can actually do things with you. They interact with 3D spaces, they pursue complex goals, and they learn on the fly. And the testing ground they're using to figure this all out is honestly what makes this so compelling.
That's video games, right?
Exactly. To teach these AI models how to eventually operate physical robots out in the real world, researchers are just dropping them into rich commercial video games.
So not just like a flat 2D grid or a basic maze anymore.
No, not at all. They're dropping them to massive 3D titles like Valheim, No Man's Sky, and Minecraft.
Okay, let's set the context for why this is even necessary. Because, we have AI right now that can pass the bar exam, right? Or summarize a 1,000-page legal document in a few seconds.
Which is incredible on its own.
It is. But if you ask that same genius-level AI to, say, clear a dinner table, it completely fails.
Totally falls apart.
It doesn't know how to move its arm, it knocks over the water glass, and if a chair is moved like 2 inches to the left, it just gets completely confused.
Yet what you're pointing out there is a really famous concept in computer science. It's known as Moravec's paradox.
Moravec's paradox.
Right. It's this observation that high-level cognitive tasks like playing grandmaster chess or, passing the bar are actually relatively easy to compute.
Which feels backwards.
It does feel backwards.
Yeah.
Because the low-level sensor motor skills like navigating a cluttered living room or picking up a fragile coffee cup without crushing it, those require massive amounts of subconscious computational power.
Wow.
Yeah, our most advanced foundation models have historically struggled with this because they are fundamentally disembodied.
They don't have bodies.
Exactly. They're trained on static text and images. So they can perceive the world, sure, but they cannot act within it. They don't really understand the physical consequences of taking an action in a 3D spatial environment.
Okay, let's unpack this because it's like having a supercomputer brain trapped in a glass jar on a desk.
That's a great way to look at it.
Right, like the brain can recite the encyclopedia backwards, but it can't even tie a shoe because it has no hands and, well, no environment to actually practice in.
Exactly. And to get beyond that limitation, an AI needs agency. It has to be able to take an action, observe how that action changes the virtual or physical world around it, and then update its understanding based on that consequence.
And that loop is what this new model is doing.
Right. That loop is what SIMA 2 is engineered to master.
Yeah.
And by the way, SIMA stands for Scalable Instructable Multi-World Agent.
Got it. But there was a SIMA 1, right?
There was, but SIMA 1 was really just a proof of concept and is highly limited. It could follow rigid, simple commands like go to the campfire.
Okay.
But it didn't really reason. If it saw a campfire in a totally new game and it looked slightly different from its training data, the agent just froze. It didn't know what to do.
Oh, wow. So SIMA 2 fixes that.
Yeah, SIMA 2 bridges that gap entirely. It acts as a genuine interactive partner.
The detail that stands out immediately in this DeepMind report is how they constrain the agent, because SIMA 2 does not cheat.
No, it has zero access to the underlying game code.
Wait, what do you mean by cheat? Like, how do other AI agents cheat in video games?
Well, traditionally, when researchers train an AI to play a game, they give the model direct access to the game's API.
Oh, I see.
Yeah, so the AI is fed the exact mathematical coordinates of every object, every enemy, every wall in the game state. It isn't actually seeing the world like we do.
It's just reading a spreadsheet.
Exactly, a spreadsheet of exact locations. But SIMA 2 does not get that luxury. It plays under the exact same constraints a human player does.
That's wild.
Right. The agent is just fed a stream of video frames, literally a 720p screen of pixels, just raw visual input.
And for the output,
For output, it uses a simulated 96-key keyboard and a mouse interface.
a virtual keyboard and mouse.
Yep. It has to generate the digital signals to move a mouse, click, and press WASD to walk around.
See, that constraint forces the model to develop true spatial intelligence because it has to look at a flat 2D array of pixels on a monitor and deduce the 3D geometry of the room entirely on its own.
It really does. But giving an AI a virtual keyboard and a screen, that's only half the battle.
Right.
I mean, a pocket calculator has a keyboard, but it doesn't know why it should press the space bar to jump over a virtual log. The model has to actually understand the causal relationship between its intent and its physical keystrokes.
So how does SIMA 2 actually process that information under the hood? Like you have an AI looking at pixels and pressing buttons, but there has to be a mechanism translating the visual input into a physical decision.
Well, the architecture is built on a foundation model called Gemini Flashlight.
Okay.
And because it uses a vision language model at its core, it inherently understands what objects are and what human language means.
Right. It already knows what a tree is.
Exactly.
Yeah.
But to teach it to act, DeepMind trained it on a massive mixture of data. A large portion of this was raw human gameplay.
Like Twitch streams.
Basically, yeah, recording humans playing these 3D games while annotating what they were trying to accomplish.
Right.
But here's the problem. Raw gameplay data just shows actions.
Right. It just shows the result.
Exactly. It shows a human pressing a mouse button and a character on screen swinging an axe. It does not capture the cognitive process of why the human decided to swing the axe at that exact moment.
Because the human brain makes, a dozen subconscious calculations before clicking that mouse.
Exactly. So to bridge that gap, DeepMind developed something they call bridge data.
Bridge data.
Yes. The researchers used a much more powerful model, Gemini Pro, to analyze high-quality human gameplay videos. And they used it to artificially synthesize an inner monologue for the data.
Wait, an inner monologue.
Yeah, they generated a text-based reasoning track that explicitly connects the user's overarching instruction to the visual scene and then maps that to the physical action.
Wait, so the AI is basically talking to itself in the background.
Pretty much, yeah.
Let me make sure I'm visualizing this correctly. It sounds like an Olympic downhill skier standing at the starting gate.
Oh, okay, I like that.
Like before they push off, you often see them physically leaning left and right, and they're whispering to themselves out loud, like, okay, sharp left at the pine tree, tuck for the jump, absorb the landing.
Right.
They're verbally narrating their physical actions to prime their nervous system before they actually execute. Is that basically what this inner monologue is doing for the AI?
That is a highly accurate analogy, actually. The bridge data trains the agent to interleave its modalities.
Interleave.
Yeah, so instead of just taking an image and immediately spitting out a blind mouse click, the agent is trained to output chunks of data in a very specific causal sequence.
Okay, what's the sequence?
First, it generates internal reasoning, a text output that exists in its processing pipeline, but isn't shown to the human user.
The skier whispering to themselves.
Exactly. Then, if the task requires it, it outputs external dialogue to speak to the user. And finally, it translates that internal reasoning into precise mouse and keyboard coordinates.
Wow.
All of these outputs are causally linked to the current 720p image it is processing. This sequence forces the model to articulate its thought process before committing to an action.
Okay, let me play devil's advocate for a second here.
Go for it.
When it generates this inner monologue, does it actually understand the game environment, or is it just pattern matching? Like, is it just spitting out the next most likely text token, which just happens to correspond to the code for jumping over a log?
That is a vital distinction. And the evidence points heavily toward genuine spatial understanding, not just mere pattern matching.
How do we know that, though?
We know this because of how it handles novel situations. If it were just pattern matching, it would fail the moment the environment stopped looking exactly like its training data.
Which is what SIMA 1 did.
Exactly. But by forcing the model to generate that intermediate text reasoning, it aligns its latent space, its abstract understanding of concepts like obstacles or danger, with the physical output.
Ah, I see.
It isn't just memorizing a sequence of buttons, it is reasoning about the physics of the pixels on the screen.
Here's where it gets really interesting because the inner monologue training is what takes this from a theoretical exercise to actual observable behavior inside these games.
Yeah, the test results are incredible.
Right. DeepMind ran tests where they gave SIMA two instructions, and the resulting interactions read like you are literally playing with a human co-op partner.
They really do.
There's this one test run inside the space exploration game No Man's Sky. A user types a prompt to SIMA2 saying, "Can you go check out those egg-shaped objects and tell me what material they are made of?"
And just think about what that instruction requires. It requires visual identification of an abstract shape, spatial navigation across uneven terrain, and information retrieval.
And we can actually read SIMA2's inner monologue during this test.
Yeah, which is the best part.
Internally, the AI processes the visual frame and generates this text. The user wants me to identify the material of egg-shaped objects. I need to locate these objects first.
Which is perfect reasoning.
It is. It then generates the keystrokes to walk the character over to the objects. It looks at the screen, visually reads the game's pop-up text that appears when you stand next to the item, and then generates an outward reply to the user. It says, "I found the objects. They appear to be plants containing carbon."
This fundamentally changes how we think about interacting with machines.
It really does.
This is embodied dialogue. When you ask a normal chatbot a question, it just searches a static database for the answer, right?
Right.
But SIMA 2 had to physically navigate a 3D spatial environment to acquire the information requested. The knowledge was tied to a physical location.
And it applies that same reasoning engine to basic logic puzzles too. Like in another test, a user tells the agent, "Go to the house, colored like a ripe tomato."
And notice the instruction doesn't contain the word red.
Exactly. But the AI's inner monologue triggers. It notes that a ripe tomato is red. It scans the 720p stream of pixels, identifies a red house down the street, and generates the keystrokes to walk to the front door.
And because of the multimodal nature of the Gemini Foundation model, this reasoning isn't restricted to just text.
Right, the sketch test.
Yes. DeepMind's researchers decided to really test the limits of this abstract reasoning by handing the AI a crude red sketch of a tree.
The sketch example is where the cognitive leap becomes incredibly apparent because the user just uploads a drawing of a tree that looks like, a child scribbled it in MS Paint.
It's very basic.
And the instruction is simply, find an object of the kind that is drawn in the sketch above and interact with it in an appropriate way.
And SIMA 2 takes that 2D image prompt and cross-references it with the 3D game world it is currently observing.
Which is huge.
Right. It has to visually map the abstract red scribble to a complex 3D rendering of a tree in the distance. It navigates over to the tree, reasons that the appropriate interaction for a tree is chopping it down, equips an axe from its inventory, and executes the fine motor control to swing at the trunk until it falls.
So let me ask the big question. Why does it matter that an AI can chop down a virtual tree based on a drawing? What does this actually mean for you, the listener, who is trying to understand where this technology is heading?
Well, it proves that the system successfully combines abstract reasoning with spatial intelligence and fine motor control.
Okay.
Recognizing that a red scribble represents a physical tree requires high-level abstract reasoning.
Right.
Locating a matching tree in a dense 3D environment requires spatial intelligence. And then equipping the axe and clicking the mouse at the correct angle and rhythm requires low-level motor control.
And it's doing all three at once.
Exactly. By fusing those together, you get an agent that can execute multi-step, ambiguous instructions without step-by-step hand-holding.
Which is the dream.
The researchers demonstrated it, handling prompts like, go up to the second floor, turn left into the room with the tentacle, and at the end of the hall, get the VR headset.
That's a lot of steps.
But it decomposes that goal, executes the sequence, and reports back. And that cognitive process is exactly what you need for a physical robot operating in your house.
You want to be able to say, go upstairs, find the blue laundry basket, and bring it to the washing machine.
Precisely. It's the exact same computational challenge, just applied to a physical living room instead of a virtual space station.
But, playing games you have been heavily trained on is one thing. If an AI analyzes 1,000 hours of No Man's Sky data, it will eventually get good at No Man's Sky.
Naturally.
True intelligence is measured by how a system handles an environment it has never encountered before.
Absolutely. Generalization is the holy grail of this research. Can the spatial and reasoning skills learned in one specific environment transfer to a physics engine or an art style the agent has never seen?
To test this, DeepMind dropped SIMA2 into entirely new games that were strictly held out from the training data. We are talking about games with totally different mechanics and user interfaces.
Right, completely alien environments to the AI.
They used Aska, which is a Viking survival game, Mina Dojo, a testing suite built inside of Minecraft, and The Gunk, a story-driven sci-fi puzzle game.
And remember, SIMA 1 failed this kind of test completely.
Right.
If the textures changed, its pixel matching algorithms just broke down. It couldn't recognize a campfire in Aska because the rendering engine made the fire look different from the campfires in its training set.
But SIMA 2 adapted immediately. Because it relies on its inner monologue and general world knowledge rather than just rote memorization, it thrived.
It did.
Like in Minecraft, it successfully navigated the blocky terrain, it mined coal with a pickaxe and fought off zombies using a sword and shield, and it was narrating its strategy internally the entire time.
Which is amazing. But the Gunk is where it showed real-time learning.
Oh, the suction tool.
Yes. It encountered a completely new game mechanic, a handheld suction tool. It had zero training data on how this specific tool worked.
So how did it figure it out?
Well, how it solved that problem is a perfect demonstration of vision-language integration. It looks at the screen and visually identifies a pop-up text prompt that just says AB sorb.
Okay.
Because it has a large language model at its core, it cross-references the word absorb with its vast internet training data regarding suction and vacuums.
Wow.
Yeah, it maps that conceptual knowledge to the sustained physical action of holding down the left mouse button. It figured out how to clear the alien gunk just by reading context clues.
It learned a new physical mechanic exactly the way a human player learns a new game.
Exactly.
But the ultimate test of generalization in this report wasn't dropping the AI into a pre-existing commercial video game. It was the integration with Genie 3.
Oh, Genie 3. Yeah, this is where it gets really sci-fi.
Right, because Genie 3 is a conditional world model. It doesn't rely on a traditional game engine. It generates limitless, photorealistic virtual worlds on the fly.
Right. You provide a text prompt or just a single image. And Genie 3 generates a fully playable 3D environment frame by frame.
The environment literally does not exist until the moment it is generated.
And DeepMind took SIMA 2 and dropped it inside these Genie 3 environments.
Which is just mind-bending to think about. You have one AI generating a photorealistic urban street or a dense forest in real time, and another AI walking through that hallucinated space, treating it like a real physical environment.
It navigated around parked cars and walked through forests that were being dreamt up on the spot.
It's incredible.
It really is. And this creates a massive virtuous cycle for AI training. Because, one of the primary bottlenecks in developing physical robotics is the scarcity of training data.
It's expensive to build robots.
It is expensive, slow, and potentially dangerous to train a physical robot in the real world. But if Genie 3 can generate infinite photorealistic environments with varying physics and layouts.
And SIMA 2 can act as a generalist agent practicing inside those worlds.
Exactly. You create an endless, perfectly safe training pipeline. The agent can experience millions of edge cases, different staircases, different lighting conditions, different physical obstacles, before that software is ever downloaded into a metal chassis.
There is a massive technical hurdle here, though, that we have to address. Because if you take a genius-level AI, a model capable of passing advanced math exams and writing complex Python code, and you force it to spend all of its computational cycles learning how to jump over rocks, swing axes, and navigate video game menus, does it lose its original intelligence?
That is the big question.
Right. Does the physical training overwrite the intellectual capability?
It is a severe problem in machine learning. It's known as catastrophic forgetting.
Catastrophic forgetting.
Right. When researchers take a large language model and fine-tune it purely on physical actions, creating what we call a vision language action or VLA model, the model often forgets how to talk or reason entirely.
Wow, it just loses it.
Yeah, because the action data, which is just endless sequences of mouse clicks and keyboard presses, is radically different from the semantic text data it was originally trained on. The new physical pathways literally overwrite the neural pathways used for complex logic.
But the data from the DeepMind report reveals that SIMA 2 managed to bypass catastrophic forgetting almost entirely.
Which was a huge relief.
They ran the agent through a gauntlet of standard AI benchmarks to test its cognitive retention. And they didn't just ask it basic trivia. They tested it on live code bench to measure its ability to write functioning software.
A very tough test.
Yeah. They tested it on the AIM benchmark, which requires multi-step mathematical reasoning that even advanced college students struggle with. And they tested it on GPQA, which measures PhD-level scientific reasoning.
And the results showed almost zero regression compared to the baseline Gemini model it was built on.
Almost zero.
Right. It retained its high-level cognitive abilities while simultaneously mastering low-level physical control.
So it can play Goat Simulator perfectly and still solve complex calculus. And because it retains that high-level intelligence, the DeepMind researchers were able to implement a really fascinating architectural setup at the end of the report. They created a manager-worker dynamic to solve the problem of long-term memory.
Yeah, this is a brilliant solution because SIMA 2 is built on Flashlight, which is a lightweight model optimized for extreme speed.
It has to be fast.
It has to be.
Yeah.
It needs to react instantly to the game environment. Swinging a sword at an enemy or jumping across a moving platform requires millisecond reaction times.
But there's a trade-off.
There is. The trade-off for that speed is a very short context window.
Yeah.
It doesn't have the memory to remember what it was doing 20 minutes ago.
So for long-horizon tasks like building a complex shelter over the course of an hour, it needs a manager.
Precisely. DeepMind paired the fast reactive SIMA 2 model with Gemini Pro, which is a much larger, slower, but highly intelligent model.
Let's map out how this actually functions. If Gemini Pro is the architect looking at the blueprint and saying, build a wall here, then SIMA 2 is the bricklayer on the ground.
Just focusing on the immediate task.
Right, just focusing on putting the mortar on the next brick and making sure it is straight.
That's exactly it.
Yeah.
And the mechanism driving this is a polling system. Every K steps, roughly every few seconds of gameplay, the Gemini Pro model takes a snapshot of the screen.
Okay.
It acts as the system's long-term memory buffer. It assesses the overarching goal, evaluates the progress made by the bricklayer, and issues a high-level text instruction.
So it might say, you have successfully gathered the wood, now navigate back to the crafting table.
Exactly. SIMA 2 receives that high-level token, decomposes it into the necessary low-level mouse clicks and keyboard presses, and executes the physical movement.
That is so smart.
It really is. This hierarchical token passing setup unlocks massive, long-horizon task completion that neither model could physically achieve on its own.
When you step back and look at the whole picture, the trajectory here is just staggering.
It really makes you pause.
We have moved from AI being a passive text box waiting for a prompt to an active embodied agent with an inner monologue. We are looking at a system that can process a crude sketch, reason internally about its spatial geometry, generate a multi-step plan, and navigate an infinitely generated 3D world to execute that plan.
All in real time.
All in real time, using visual inputs and virtual keystrokes, mimicking human interaction perfectly.
And, connecting this directly to you, the listener, and why this research matters for the immediate future. Knowledge is only valuable when it is applied.
Right.
For years, AI has possessed vast encyclopedic knowledge, but lacked the physical application. SIMA 2 proves that we have successfully bridged high-level reasoning with low-level physical control, and done so without destroying the model's core intelligence.
The video games are merely the sandbox.
Exactly. The skills being perfected right now, spatial awareness, real-time visual adaptation, tool use, and following ambiguous multi-step instructions, these are the precise foundational skills required for the physical robots that will soon operate in our homes, our hospitals, and our logistics centers.
Which leaves a final thought for you to mull over based on the implications of this report.
Go on.
The document notes that SIMA 2 has the underlying capacity to autonomously generate its own tasks and self-improve without human prompting.
Right. It can just keep going.
Yeah. So if you combine an AI that can endlessly self-correct and learn new mechanics, and you drop it into a conditional world model like Genie 3 that can generate infinite, perfectly realistic physical environments.
Where are you going with this?
Well, is it possible that the first fully capable general-purpose physical robot won't achieve its mastery by practicing in a laboratory? It seems entirely possible that the AI will achieve physical mastery by living a million lifetimes inside a simulated matrix before its code is ever downloaded into a physical metal body.
Oh, wow. Yeah, the boundary separating simulation training from physical reality is getting vanishingly thin.
Yeah.
And the speed of that convergence is only accelerating.
Next time you are wandering around a video game, take a second to consider what might be learning right alongside you. Thank you for joining us on this deep dive. Keep questioning the systems around you, keep exploring those multiple perspectives, and we will catch you on the next one.